Hello and welcome to Coderific. In this program, we are going to use MNIST Dataset once again, and we are going to write a model and train it so that it is able to predict the labels of each image. As you know that MNIST Dataset has handwritten images in different patterns. For example, 5-digit appears multiple times here. You can see that each of the 5 has different pattern, but it will have same label, which is 5. And to predict those labels, we are going to write a program for regression and classification, and then we will decide which one works better in case of the prediction of labels. So let's start programming. So I am back to my Spyder editor of Python. As you can see that I have already imported some of the important libraries and written few lines of code as initials of my training model. If you notice, these are the convolution blocks that I took from Autoencoder video. I will add the link to this video in description box, and I prefer to watch that, how we design an autoencoder, and the same function I have used from that video, which I will use to analyze the prediction of my trained model. So because I am going to work on MNIST images, and the dimension of each image of MNIST is 28 by 28, and it is grayscale, that's why I have reshaped it to 1. The first convolution block has output number of filters 16, followed by 2 convolution blocks that have similar number of filters. And if you notice that for every convolution block I have used the activation value. So I have run my program written so far here, and if I run code underscore layer, which is my last layer, and you can see that the output of this layer is 4 by 4 by 8. Output number of filters 8 that have dimension 4 by 4. From this max pooling layer, I am not going to include any other convolution layer, and from here I am going to flatten this output. Then on this flattened output, I am going to perform dense function, which will generate a linear array of size 128. I am going to perform another dense, which will reduce the dimension of linear array from 128 to 64. And the final output I will get as one scalar value, and that will be extracted by performing the dense on the output 64. Now I am going to call my model, which is based on the input layer, which is 28 by 28 by 1, and the predictions will be, which will be a scalar value for every input. Now I am going to upload the MNIST dataset. So I have used MNIST.npz variable dataset, which will generate 4 subsets, and I have created 4 variables to hold these 4 subsets. In my variable explorer, you will see that the format of input image is unsigned integer, but in my trained model I prefer using float image, so I need to convert this into float. To convert these values into float is the best way to divide these values by the maximum pixel value, which is usually 255. I'm going to run this. You can see that my input images are now in format of float 64. Next, I am going to convert my labels for each image into float. If you only call float over ytrain or ytest, it will give you a scalar value error. So in this line, basically I am fetching each element from y_train and converting it to float, and after conversion I am passing it to ytrain. As you can see that the converted float array is in the format of list, but before I proceed, I need to convert this list to array. So calling np.asArray over list of y_train, I can convert a list into numpy array. Now you can see that the format of my ytest and ytrain float values are in the format of numpy array. Once I have pre-processed input dataset, now I have pasted the same settings to train my model that I used in the autoencoder video. As optimizer, I am going to use HSD with the defined parameters, as you can see in this line, and as a loss I have called it mean squared error, because for now I am going to do an experiment in which I will train my model as a regressor. And what do I mean by regressor? For example, that as we can see, my input image is 28 by 28 by 1, and for each of this image is one scalar value as a label. I am not going to convert it into one hot encoding labels or any other type of labels, I am going to use these scalar values as it is to be predicted by my model. So that is why I have used the loss as mean squared error, and I have used the same model checkpoint which will monitor the loss and will save the best only that has minimum loss. And over the fit section I am going to call timing so that I know how much time it took to train. Remember that I have called the time over only the training process. It does not include the time that engaged us in pre-processing of our input dataset. Once the model is trained, I am going to print the time it took, and here I have used an epochs initially and used batch size 128. I have kept shuffle true. Let me tell you that if you keep the shuffle false, sometimes the network makes pattern inside the memory and start learning from that, which will cause the training or validation loss increased. So for validation dataset, I am going to use the 20% of my extrained dataset, and I have kept the variables 1 because I like to see the progress. In the same way, I like to see the values inside the variables and the type of it. That's why I love this Spyder editor of Python. After the network is trained, I would like to use this model to predict the labels over test dataset, and I have kept the batch size lesser than the batch size I used in training process, because if you change the batch size in prediction, it will not cause any difference in the final predictions. So I'm going to run my model written so far here. Model has finished training and it took 321 point something seconds. If you want to see the time in minutes, simply divide this time by 60. See that the model training took 5 minutes. And to perform mean squared error over predicted and ground truth values, we can analyze it, but right before it, first we need to confirm the correct format of y underscore predict array. So as you can see in my variable explorer, array has added extra dimension, and if we compare this with the y test, you can see that it is a linear array. To compare these two arrays, we need to remove this extra dimension from this array. And to do that, I'm going to reshape the y-predict, keeping only the first dimension. Now you can see that the y-predict and y-test datasets are in the same linear format. I'm going to call the mean square error. You can see that the RMSE is 5 point something, which is not very great. It means that it is not predicting the correct values for our test dataset. And if we want to verify, we are going to see that for y test element at position 5 what it has predicted. So you can see for my image that is handwritten image of digit 1, it has predicted the 0 level. So before I jump to classification problem, I want to try another quick solution that came into my mind. I am going to ignore SGD optimizer and using Adam instead, and keeping the rest of the settings same. Let's train our model again. You can see that the model has finished training, and by changing only one parameter of optimizer from SGD to Adam, you can see that the loss has minimized, and up to last epoch, which is 10, and we got the minimum validation or training loss up to 0.4 from 28 that we got from previous training. And you can see that the RMSE is also reduced from 5 to 0.68, but still the RMSE is not very good. RMSE is still not very good, and you can see for true value 1 it has predicted the wrong value. So we can say that the regression is not an ideal situation in which we want to predict the labels. Let's take an example of handwritten digit 7, and for example it appears 10 times in dataset with different patterns, and for each of these 10 times the label will be same, which is 7. And in my point of view, why the regression did not work well, because there is a lot of redundancy in the labels, as I gave you the example of handwritten digit 7. So the best solution is to use these such format of labels as a OneHotEncoded vector and train the model as a classification. So to train the model as a classification, first thing I am going to change my output from one scalar value to a vector of size 10. This time my model will return prediction or the probabilities over 10 classes starting from 0 to 9, because we have 10 images with the corresponding labels. If you have a scalar value as your output, ReLU activation will be good for the final prediction, but here we have a vector value as our output, so I am going to change the activation from ReLU to softmax, because softmax activation function works better in scenario of vector format of our output. And to train my model, I'm not going to use scalar values of labels. Instead of that, I'm going to use OneHotEncoded labels. So I will generate a function which will convert our scalar values of targets into OneHotEncoded labels. And to use the OneHotEncoder function, I have imported scalar or preprocessing library. Now I am going to write the function. This function will take the input values which are in currently scalar values. First, I have created the object of OneHotEncoder into OneHotEncoder variable. Next, using the same object, I have called fit_transform function, which takes array of 2 dimensions. Right now we have the y-test dataset into 1 dimension, and to convert it into OneHotEncoder, I have added 1 extra dimension at the end, keeping the original shape. XYZ will carry the OneHotEncoded labels. Finally, I'm going to return the OneHotEncoded labels. I forgot to mention one more thing which is very important, that this line will generate sparse matrix that you cannot access it as input dataset. To convert this matrix into numpy array, you need to call dot to array function so that the matrix is converted to a numpy array. You can see I have called the same function for ytrain and ytest and replaced the scalar values of labels with the OneHotEncoded labels. Next, I'm going to change my loss function from mean squared error to categorical cross entropy, because now my labels are not in scalar but instead they are in the format of categorical labels. For now, before converting them into OneHotEncoded labels, you can see that the labels are in the format of scalar values that directly says what is the target value for the corresponding 700 digit, and I am going to replace the old values of these two datasets with the new one that are OneHotEncoded labels. Now you can see that the format of our output OneHotEncoded labels is 2 dimensional, and if I click on its value, you can see that the every category is expressed categorically. For example, in first row, all of the columns are 0 except the column 7, which means that this image belongs to image 7. Similarly, if you look in the second row, which is index 1, you can see that all of the columns are 0 except the column 2. It means that this image belongs to handwritten digit image of 2. So now I have converted my labels into OneHotEncoded labels, and to train the network, I have used the same optimizer that we saw in previous training. I am going to keep an eye on accuracy, and this time, because I am going to train my model as a classification, in ModelCheckpoint I am going to use the accuracy, and the mode will be maximum accuracy. And to save the mass model, the ModelCheckpoint will use the maximum accuracy value after every epoch. So I am going to remove the rest of the lines before prediction, because the prediction method is same. It will generate the OneHotEncoded labels. Let's first run our model. Since my model is running, I want to take advantage of this time to explain you some things. As you can see that now this time I'm going to train the model as a classification. I have changed the name of my saved model. Keep an eye on the saved model every time you change the parameters and start training your model from scratch. Otherwise, the ModelCheckpoint always will restore the weights from previously stored model with the same name. So don't forget to change the name of model every time you change the parameters and start the training from scratch. You can see in my IPython console that the model has finished training, and total of time it took for training is 308 seconds. And if I click on y_predict values, you will see that the values are in the shape of one-hot encoded labels, and each position of label has been given a probability. To compare these results, first I want to decode these one-hot encoded labels in so that the vector values are represented in scalar format. To do that, I am going to use np.argument_max function of numpy that takes one hot encoded vector, and by mentioning the axis is equal to 1, I am going to make it a linear array. I'm going to run the same function over my y predicted values so that both of these sets are in linear formats. You can see that now my GT test, which is ground truth values of labels, are in scalar values, and similarly we can see format of predicted labels are in linear format that are converted from predicted labels of one hot encoding. Next, to analyze these results, I am going to compute mean squared error over predicted and ground truth sets. You can see the difference here in the format of RMSE values. This time the value is 0.58, and in previous settings where we used mean square error and scalar output predictions from the trained dataset, we saw that the RMSE value was 0.68. So it's a huge difference in this case. Next, I'm going to evaluate the performance in terms of accuracy. This time I'm going to use the evaluate function that takes ground truth test images and the ground truth labels, keeping the byte size 10 same every time I test the images. And I'm going to calculate the accuracy by multiplying it with 100. And you can see that the test accuracy is 98%, which is quite awesome. And to further evaluate the trained model of classification, I want to see that for ground truth value at position 0, what this model has predicted. I'm going to run this line, and you can see that for ground truth value 7, it has predicted the correct value. Before I wind up the video, let me give you a quick recap. First, we trained our network with mean squared error, keeping scalar value as a prediction, and we saw the RMSE and the validation and training losses, which were not very great. And then we converted our scalar values of labels into one hot encoded labels and trained our network with classification after converting the last layer into total number of classes. In this case, we have total classes of 10 starting from 0 to 9. To have a final prediction in terms of vector, always use the activation softmax inside the last layer. And we train the model with loss categorical cross entropy and keeping the optimizer same as Adam. Monitor the accuracy using model checkpoint and save the model with the maximum accuracy. We compared the RMSE values and training and validation losses. We saw that in case where each input image appears multiple times with different patterns but with the same label, in such scenario, if we use one hot encoded labels and train our network as a classification, we get good performance. This is it for this video. Thank you for watching. I hope you find it helpful. If you did, do like and share. Also subscribe the channel and hit the bell icon so that you get notified whenever I upload a new video. If you have any suggestions, leave them in comments section. I will do consider it. Thank you.